In this video, I'll talk about the conservation of angular momentum in rotational dynamics. Of course, because this is the angular momentum, so we're talking about the rotational dynamics. And here we have chosen one particular example of a spinning disk and a mass. So here is a spinning disk, or we can call it as a flywheel. So flywheel is basically a spinning disk and a heavy spinning disk, and it is revolving with 500 revolution per minute is given here. So initially it is 500 revolution per minute. The moment of inertia of the flywheel is also given, which is 100 kilogram meter square. Now we have a mass, and this mass is now dropped onto the flywheel. And after dropping, the mass is glued to the spinning disc, so it cannot move away from the spinning disc. It stays there. So once it is glued to the spinning disc, what should be the angular speed of the combination, or after the mass is dropped, what will happen to the angular speed? Will it increase, will it decrease, or it will remain the same? And is there energy loss, or if it is, how much is the energy loss? That's all we're going to calculate in this video. So let's write down all the given quantities first. The omega naught, which is the initial angular speed of the flywheel, is 500 revolution per minute. Whenever we're going to use the angular speed, make sure that the unit is radian per second. And as you can see, this is not the unit is in revolution per minute. That means we have to change the unit to radian per second. How do you do that? So here I have made a short note here, the revolution per minute to radian per second. The one revolution per minute I have written down in a different way here. One revolution per minute. One revolution, if an object makes one complete rotation, that means the total angle is 2 pi. And 1 minute corresponds to 60 seconds. So 2 over 60 is now 30. So one revolution per minute is now pi over 30 radian per second. So if we multiply revolution per minute by pi over 30, then it will change into the radian per second. That's what I'm doing here. Revolution per minute, and I'm multiplying by pi over 30. Now it is in radian per second. The other quantity that is given is the moment of inertia of flywheel. Here F stands for the flywheel, which is 100 kilogram meter square. The mass, the mass is 5 kilogram, and the distance to which it is dropped is 2 meter, this distance. So now once the mass is dropped, let's calculate the moment of inertia of this one. So before dropping, it does not have, so before dropping, so here we're just calculating the moment of inertia of the dropped mass here. And I was about to say, before dropping, it was not a spinning at all, so there was no axis of rotation. But now, once it is dropped, it starts spinning about the axis of rotation, so it has the moment of inertia. So what is the moment of inertia? So the moment of inertia is given by mr square, the mass, and r square. And here we assume or treat this one as just like a point mass. So all the masses are exactly at the same distance, mr square. So the mass of the dropped mass is 5 kilogram, and the distance from the axis of rotation is 2. So if you do the math, you'll get 20 kilogram meter square. So that's the moment of inertia of the dropped mass about the axis of rotation. But as there is no external torque acting onto the system, the angular momentum of the system remains constant. What does it mean? The initial angular momentum before the mass is dropped has to be exactly equal to the angular momentum of the system after the mass is dropped. That is called the conservation of angular momentum. So that's what I've written here. From the conservation of angular momentum, the total angular momentum of the system, this is for the system before dropping, and the total angular momentum after the mass is dropped. It has to be exactly equal. So before dropping, before the mass is dropped, it was not a spinning. The only thing that is spinning or revolving was the flywheel. So it has only the spinning disc or the flywheel has the only angular momentum. The mass has no angular momentum before it is dropped. Okay, so this is the angular momentum of flywheel only. But once the mass is dropped, both the flywheel and the mass starts spinning or revolving. So both has the angular momentum. So it says angular momentum of flywheel and a mass. Now, how do you find out the angular momentum? So if you recall from the again the linear motion, the angular momentum is defined as the mass times velocity. So if you need to write down this equation in rotational dynamics, then this is the linear motion, and in rotational motion the angular momentum is L, and the mass is now the moment of inertia, and the V, which is the linear velocity, will be the angular velocity. So I times omega gives you the angular velocity, or so I times omega gives you the angular momentum. Okay, so we have the I times omega naught. Here IF stands for the flywheel, and omega naught is the angular speed of the flywheel before the mass is dropped. Once the mass is dropped, then we have to take into account the both the disk or the flywheel and the mass. So this is the angular momentum of the flywheel, and this is the angular momentum of the mass. And remember, both the flywheel and the mass moves exactly with the same angular speed. It's exactly the same. Okay, the angular speed at each point of the spinning disk is exactly the same. The tangential speed might differ, okay, but the angular speed of at any point of a spinning disk is exactly the same. That's why we have written down the same angular speed for both flywheel and the mass after the mass is dropped. The the moment of inertia is given, which is 100. Initial angular speed we just calculated is 52.36 here. And now the moment of inertia is still, it will remain the same because it is still rotating about the same axis of rotation. And the moment of inertia of the mass, now we have to plug in the moment of inertia of the mass, which just calculated here 20. So that's the 20 here, and omega. And now we solve for the omega, which is 43.63. So the angular speed has decreased. Initially it was rotating or revolving with 52.36. Now it is 43.63. That makes sense because once the mass is dropped, the moment of inertia increases, and as a result, the angular momentum goes down. So I omega always remains constant. If I increases, omega goes down. In this case, I has increased, so omega goes down. That's what we call the conservation of angular momentum. Now let's find out the energy lost during this process. And you can, or in fact it is, just like an inelastic collision. And you have also studied, like when you have two cars, they collide against each other and they start moving together as a single unit. That's the perfect inelastic collision. Here exactly is the same thing. A mass is dropped, and the mass and the spinning disk now glued together, and it starts moving with a constant angular velocity. So it is an inelastic collision. So there must be some energy lost or the kinetic energy loss. So how do you find the kinetic energy? So first we find the kinetic energy by using this formula here. This is before the mass is dropped. Again, so this formula is exactly equal to half mass times velocity square. The mass is now the moment of inertia, the angular speed is now, sorry, the linear speed is now the angular speed. So you can translate this equation k equals to half mv square into the rotational dynamics. Okay, the mass has to be replaced by the moment of inertia, and the v, the linear velocity, will be replaced by the angular velocity. So once we have, then we can just plug in all the values here. What is the value of the moment of inertia of the flywheel? It is 100. The initial angular speed is 52.36. So this is the total energy before dropping. And here I have taken only account of the flywheel, not the mass. Why is that? Because this mass has no rotational kinetic energy. It is not a spinning at all, so it does not have any rotational kinetic energy. So that's the reason we just taking the flywheel. But once the mass is dropped, the mass and the spinning disk or the flywheel moves together, so both have the rotational kinetic energy. So this is the rotational kinetic energy of the flywheel, and this is the rotational kinetic energy of the mass. The M stands for the mass and F stands for the flywheel. And omega square is the same in both parts, so I'm just taking this one out. So the moment of inertia will be added together. The moment of inertia of the flywheel is 100, this is 20, and omega we just calculated here is 43.63. So plugged in all the values, and this is my final energy, and this is my initial energy. So how do you calculate the energy lost? The energy lost, or the energy difference, EF minus the final energy minus the initial energy, and we get is negative 2.28. What is the negative sign tells you? The negative sign tells you the final energy is smaller than the smaller energy. So what is the energy lost then? The total energy, this energy is lost in coupling the two objects together. Okay, so in coupling the two objects together, this much energy is lost. So this is it from the angular momentum of a flywheel and a mass. If you have any questions, write down your questions in the comment section below, and do not forget to like, share and subscribe the channel. Thank you very much.